Hey class, I just want to take a second to go over day one paper with you guys and actually post a video on how to do these questions. All right, so I'm just going to jump right on in because this is a pretty long worksheet. So number one says, if a certain silver wire has a resistance of 6 ohms at 20 degrees Celsius, what resistance will it have at 34 degrees Celsius? The temperature coefficient of resistivity of silver is 3.8 times 10 to the negative 3 per degree Celsius. And remember, the temperature coefficient is just the rate of change of resistivity with every degree change. All right, so I know that the main equation that we're going to be using is R is equal to R naught times 1 plus alpha T minus T naught, where T naught is always going to be 20 degrees Celsius and R naught is that resistance at 20 degrees Celsius. So it says that at 20 degrees Celsius, which is T naught, it's 6 ohms. So that means 20 degrees Celsius, R naught is 6 ohms. And then it says, what will the resistance be at 34 degrees Celsius? And the temperature coefficient, and this temperature coefficient only works for 20 degrees, is 3.8 times 10 to the negative third per degree Celsius. All right, plugging in my numbers, I get 6 times 1 plus 3.8 times 10 to the negative 3 times 34 minus 20. Putting everything in my calculator. Let's see. Put it over here. I want to start with what's in parentheses first. So 34 minus 20 times 3.8 times 10 to the negative third plus 1 times 6. And that gives me 6.32. So if you increase the temperature, the resistance increases from 6 to 6.32 ohms. That was number one. Number two, a length of aluminum wire has a resistance of 30 ohms at 20 degrees Celsius. At my T naught, R naught is 30 ohms. When the wire is warmed in an oven and reaches thermal equilibrium, so you put a wire in the oven, eventually it's going to have the same temperature as an oven because it reaches thermal equilibrium. The resistance of the wire increases to 45 ohms. So the resistance then goes to 45 ohms. Neglecting thermal expansion, so that wire is not getting longer or getting shorter, calculate the temperature of the oven. The temperature coefficient of resistivity of aluminum is 3.9 times 10 to the negative third. So what is the temperature? Well, we know that the temperature coefficient is 3.9 times 10 to the negative third per degree Celsius. So the equation for temperature, if I were to rearrange this equation for temperature, I would get the equation T is equal to R divided by R naught alpha minus 1 over alpha plus T naught. So it's going to be 45 divided by 30 times 3.9 times 10 to the negative third minus 1 over 3.9 times 10 to the negative third plus 20. Let me put this in my calculator. Since the resistivity went up, the temperature should have also gone up. So I'm going to put 30. 30 times 3.9 times 10 to the negative third. 45 divided by that answer. Minus 1 divided by, in parentheses, because it's scientific notation, 3.9 times 10 to the negative third plus 20. Don't forget to add that 20 because a lot of people in class forgot. So I get 148.21. Notice how I'm not rounding until the end. So do not round until you get to the end. So the temperature raised from 20 degrees to 148.21 degrees. And then resistance rose from 30 ohms to 45 ohms. All right, number 3. A wire 3 meters long and 0.450 millimeters squared in cross-sectional area has a resistance of 41 ohms at 20 degrees Celsius. If its resistance increases to 41.4 ohms at 29 degrees Celsius, what is the temperature coefficient of resistivity? First thing I'm going to write down is what is the temperature coefficient. It tells me at my T naught at 20 degrees, my resistance is 41 ohms. It also says that at 29 degrees, the resistance is 41.4 ohms. So if I take my basic equation and rearrange it for alpha, what I'm going to get is so it's going to be 41.4 divided by 41, 29 minus 20, minus 1 over 29 minus 20. Let's put this in. Let's see what we get. I get 0.00108. Or, and remember this is per degree Celsius, or 1.084 times 10 to the negative negative third per degree Celsius. Box this in. Yeah, that looks right. That's a really small number for temperature coefficient. Okay, number 4. Now, what is the resistance of a nichrome wire at 5 degrees Celsius if its resistance is 140 ohms at 11.5 degrees Celsius? This problem is interesting because it doesn't say anything about the resistance at 20 degrees. But we have to use 20 degrees because this alpha is the alpha that's for room temperature. So let's say I know T naught is always 20 degrees Celsius, but I don't know the resistance at 20 degrees Celsius. Now, I'm going to write my T and my R as the pair, the temperature resistance pair that I know. So since I know that at 11.5 degrees Celsius, my resistance is 140, let me write that down because that's a pair that I know. That was 140. But be careful because it doesn't ask us for the resistance at 20 degrees. It asks us for the resistance at 5 degrees. So I have another temperature at 5 degrees, and it wants to know the resistance there. And just so I don't get all my T's and R's mixed up, let me call the pair T1R1 and call what I'm looking for T2R2. So first thing first, I want to solve for R naught. And when I solve for R naught, I'm going to use the equation. Plugging in my numbers, I'm going to get, and for R and T, I'm going to use that pair that I got. So 140 divided by 1 plus, it gave me alpha. And then T1 is 11.5 minus 20. Putting this in my calculator, my handy dandy calculator. I'm going to do I get 140.478. All right, so that's R naught, but I'm not looking for that. I'm looking for R2, that resistance at 5 degrees Celsius. But now that I know R naught, I can use my normal equation. R is equal to R naught times 1 plus alpha T minus T naught. So I'm going to do 140.478 times, and this is R2 and T2, by the way. 1 plus, I can use this 0.4 times 10 to the negative third because I'm working with 20 degrees. Five minus 20. All right. 5 minus 20 times 0.4 times 10 to the negative 3 plus 1 times 140.478. You should get 139.64 as the resistance. Now, some of you guys might be like, wait, but when I did it the normal way, I got that. And that works for this problem, but it's not going to work like that for every problem. So just stick to this method of finding R naught. All right. Number 5. A piece of wire has a resistance of 95 degrees at 35 degrees Celsius. The wire has a temperature coefficient of 0.00640. What is the resistance at 15 degrees? All right. Start off, bam. I know T naught is 20. This question doesn't say anything about 20 degrees. What? Oh my goodness. That's okay because I can just solve for R naught. Now, one temperature resistance pair it gives us is 95 and 35. So at a temperature of 35 degrees Celsius, my resistance is 95 ohms. I couldn't use this because I don't know the resistance. In fact, that's what I'm looking for. Let me label that T1R1. And then we want to know the resistance at 15 degrees Celsius. So let me label this T2R2. Now, let's start off by finding R1. I mean, not R1. Let's start off by finding R naught. So the one pair that we know is 35/95, so it's going to be 95 divided by 1 plus 0.00640 times 35 minus 20. That's going to give me R naught. Move it over here a little bit. All right, 35 minus 20 times 0.00640 plus 1. And I get the resistance to be 86.679 ohms. And I like putting as many decimal places as possible because that's how I know my answer's going to be more precise. So now I can use the equation R is equal to R naught 1 plus alpha T minus T naught. All right, and this is going to be R2 T2. So 86.679 times 1 plus 0.00640 times T2 was 15 degrees minus 20. And you should get the resistance to be 83.91 ohms at 15 degrees. Boom, bada bang. Number 6. And I'm not going to do 7 and 8 because we did those in class, but I am going to do number 6 and 9. So a length of wire has a resistance of 50 ohms at 30 degrees. When the wire is heated in the oven, the resistance of the wire increases to 70 ohms. Calculate the final temperature of the oven. Ooh. Calculate the final temperature of the oven. So this question, again, doesn't say anything about 20 degrees. So T naught's going to be 20. I don't know my resistance at 20. My next thing I'm going to write is my temperature resistance pair. For 30 degrees, I know the resistance is 50 ohms. And I'm looking for the temperature when the resistance is 70 ohms. So this is going to be T2, R2. First step, find R naught. Remember, perfect practice makes perfect. R1, T1. 50 divided by 1 plus 3.9 times 10 to the negative third times 30 minus 20. So 30 minus 20 times 3.9 times 10 to the negative third plus 1. And then 50 divided by that answer gives me a R naught of 48.123 ohms. Now I have to find the temperature. So I have to use an equation for temperature. Now the equation for temperature is T is equal to R divided by R naught alpha minus 1 over alpha plus T naught. All right. So the resistance, this is R2, this is going to be T2, for 70 divided by 48.123 times 3.9 times 10 to the negative third. Please don't let me run out of room. Minus 1. Where's my candle? 1 over 3.9 times 10 to the negative third plus 20, because that's T0. Putting all this in my calculator. I pray that it's right. 3.9 times 10 to the negative third times 48.12. Wait, 48.12. Oh, no, that's wrong. We got the glare. 3.9 times 10 to the negative third times 48.123 gives me that. 70 divided by that answer gives me that, minus 1 divided by 3.9 times 10 to the negative third plus 20. And I should get 1.36.57 degrees Celsius, which is pretty hot. All right, quickly, number 9, because my phone's on 5%, and I don't want it to die in the middle of this video. All right, a metal wire has a resistance of 10 ohms at a temperature of 20 degrees Celsius. If the same wire has a resistance of 10.55 ohms at 90 degrees Celsius, what is the resistance when its temperature is negative 20? So, good news here. It tells me that my temperature, so at 20 degrees Celsius, the resistance is 10 ohms. You might be wondering, this is a normal problem. Well, hold your horses, no time. All right, and then it says at 90 degrees, it's 10.55 ohms. What is the resistance at negative 20 degrees? Now, you would think that, oh, why don't we just use our normal equation of R is equal to R naught 1 plus alpha T minus T naught. Well, this would be fine to use except for one thing. This question doesn't give us the temperature coefficient. What? So, now the first thing we have to do, instead of finding R naught, we just need to find the temperature coefficient. And the equation for that is R divided by R naught, T minus T naught, minus 1 over T minus T naught. All right. So it's going to be, I'm going to use T1 and T1 and R1 in order to find that temperature coefficient, because I can't use T2, R2 because I don't know R2. So it's going to be 10.55 divided by 10 times 90 minus 20 minus 1 over 90 minus 20. And that's going to get me, let me do 90 minus 20 times 10. 10.55 divided by that answer. Then we do minus, what's 90 minus 20? 70. Minus 1/70th. That's going to give me 7.85 times 10 to the negative fourth. Oh, sorry, not 7.85, 7.857. I like 3 decimal places. Times 10 to the negative fourth. Now that I know alpha, I can actually find that resistance. So now what I'm going to do is I can use this equation. When I use this equation, I know R naught. R naught was 10. 10 times 1 plus, oh, I know alpha now.